All right, so now we're talking about matrix solutions to linear systems. There is a relationship between systems of linear equations and matrices. Matrices are a rectangular array of numbers which play a central role in representing computer images. Matrices are used to display information and solve linear equations. An augmented matrix has a vertical bar separating the columns of the matrix into two groups. The coefficients of each variable are placed to the left of the vertical line, and the constants are placed to the right. If a variable is missing, its coefficient is 0. So horizontally, they are rows, vertical are columns. So if we're looking at a systems of linear equations, and this is going to be the augmented matrix. So this is similar to determinants. We're just pulling the coefficients. So 2, -3, 6, 1, 1, 0. And we put that bar in between the variable coefficients and the constants. So this one would be 3, 1, 2, 31, 1, 1, 2, 19, 1, 3, 2, 25. We will zero fill if needed. So if this is our system and this is our augmented matrix, we have 1, 2, -5, -19. We don't have any x's, so 0, 1, 3, 9. The last one we have no x's, no y's, we just have 1 z and 4. Now this here is the goal to actually solve the matrix to this, where the last variable is solved and then substitute this value to find the value of the other variables. This is just like solving the system of linear equations. So we could solve for our z equals 4. We get to that 1, 4, and we take it back to a system. We get z is equal to 4, then plug 4 back in to this to figure out what y is, and then take the z and the y and plug it back in. So the third row gives us the value of the one variable, and we'll sub back into that. We also have row operations. So the matrix row operations, we have, if two rows are switched or interchanged, where they're going to just kind of change about, we just do a double arrow in between them. And we're going to label our rows. We can also multiply by a non-zero number times a row, similar to what we were doing in the systems of equations where we talked about what we were multiplying it by. We'll actually put it in front of a row number now. The elements in any row may be multiplied by a non-zero number and then added. So we're only going to multiply and add. Those are our two, or we can switch the rows, but otherwise we're not doing anything else. Two matrices are row equivalent if one can be obtained from the other by a sequence of row operations. Gaussian elimination, we're going to write the augmented matrix, and then we're going to use those row operations. We need to get a 1 here, then get a 0, then get a 0. Then we'll get the 1 here and get a 0 below it. And then we need to get a 1 right there. So I've written the goals that we're looking for is row 1. The first number is equal to 1. Then you need to get row 2 and row 3's first numbers to 0. Then row 2, we need to get a 1. And then get row 3, second number, to be a 0. And then row 3, the third number, equals 1. Then we'll write the system of linear equations corresponding back to the matrix in step 2 and use back substitution to find it. So this is our goal, what it looks like right there. This is wording it out like what we're looking for. There is more than one way to reach the goal. It just depends on which operations you choose to do and the order you actually choose to do them in. So you can get to the same answer but in different ways. All right, so let's go work some matrices. So example 1, we're going to use matrices and Gaussian elimination to solve the system. So we're going to use matrices to solve the system. It's also using Gaussian elimination, but I don't really want to write Gaussian elimination. All right, so if this is our system, so this is a system we've been seeing, systems, through this entire section. So x plus 3y equals 5, and 2x minus y equals negative 4. What we need to do is write the matrix that corresponds with this. So our matrix is going to be the coefficients here. So 1, 3, 5, and 2, negative 1, negative 4. So it's similar to what we've been doing in determinants, just a little bit different. So remember, our first goal was to get a 1 up in that top corner. And yay, we already have a 1 there, so we're good on that first goal. The second one is to get this to be a 0. So how do we make 2 become a 0? Well, we need to add a negative 2. So where can we get a negative 2? We can use this row up here and multiply 1 times negative 2. We add it to 2, we'll get 0. So that gives us an idea of what we're going to do. So we're going to do negative 2 times row 1 plus row 2 will equal our new row 2. I add a little bit more in the operation so we can actually see what we're trying to do, because I tell us what that's going to become. All right, so negative 2 times row 1, we're going to have negative 2 times 1, negative 2 times 3, and negative 2 times 5. So 1, 3, and 5 are each getting multiplied by negative 2. So this will get us negative 2, negative 6, and negative 10. And now we're going to add row 2, which is 2, negative 1, negative 4. So 2, negative 1, negative 4. Negative 2 plus 2 will get us 0. That's the number we wanted. Negative 6 minus 1 is negative 7. And negative 10 minus 4 is negative 14. So let's rewrite our matrix. So we used the first matrix, but we didn't do anything to it. Or the first row, we used it, but we didn't change it. So it's still 1, 3, and 5. But now we have 0, negative 7, and negative 14. So this row stays the same. The only thing that changes is our new row 2. So now what we need to do is get row 2 to have a 1 right here. So how can we get negative 7 to be a 1? Basically, we look at it, well, if we divided by negative 7, we could get to 1, but we don't divide, we multiply. So instead of looking at it as division, look at it as multiplication. So we can then do negative 1 over 7, well, that's like dividing by a negative 7, times row 2. And that'll get us our new row 2. Since we're only dealing with row 2, I'm not going to write equals row 2. So negative 1/7 times row 2 will get us negative 1/7 times 0, negative 1/7 times negative 7, and negative 1/7 times a negative 14. So anything times 0 stays 0. Negative 1/7 times negative 7 becomes a 1, and negative 1/7 times negative 14 becomes a positive 2. And when you're doing this math, you can look at, this is 14 divided by 7 because it's got a 1 on top, and you can put the 14 on top. But you need to understand in the operations of matrices, there's limits on what we do. So our matrix then will be still 1, 3, and 5, but now we have 0, 1, and 2. So now we've got a matrix. Let's rewrite the system. So our system now looks like this. We have 1x, 3y, and a 5. So this will become x plus 3y equals 5. And then we have y is equal to 2. Well, we know what y is, so let's sub y equals 2 back into our only other equation. We will have x plus 3 times 2 equals 5. So x plus 6 equals 5. Subtract our 6 over, and we end up with x is equal to -1. So we have -1 for our x, 2 for our y. It's an ordered pair, and you can check this by plugging it back again into the original system. So that's the start of matrices. That's one problem starting from the beginning with our system. Let's go look at another one. So example 2. We've got our system, and our system is going to be 4x minus 3y equals 11, and 3x plus 2y equals 4. And let's write our matrix. So the matrix is going to be 4, -3, 11, 3, 2, and 4. Now we've got to figure out, remember our goal. Our first goal is to have a 1 right there. We don't have a 1, but we've got to make it into a 1. But we can use some multiplication process. If you divide by or multiply by 1/4, when you do that, you're going to get some really icky fractions over here. So we don't want to multiply by 1/4 because then we'll deal with fractions, and that'll make this really hard. However, if I look at this as 4 minus 3 equals 1, I could multiply this row by -1 and add it to that row. So that's what we're going to do. So always think about what you're going to choose to do. So -1 times row 2 plus row 1 will equal our new row 1. So -1 times row 2 will be -1 times 3, -1 times 2, and -1 times 4. So that's -3, -2, and -4. And now we will add row 1, which is 4, -3, and 11. That'll get us 1, -5, and 7. And rewrite our matrix. So our new row 1 is 1, -5, and 7. But row 2 is still the same. We used it, but we didn't change it. So 3, 2, and 4. So now we have our 1. We now need a 0 right there. So to get this to be a 0, I need to subtract 3. Well, I can use the 1 I created here and multiply by -3 to get that to become a 0. So we will now do -3 times row 1 plus row 2 will get us our new row 2. So -3 times row 1 will be -3 times 1, -3 times -5, -3 times 7. So -3, +15, -21. And now we'll add row 2, 3, 2, and 4. So -3 plus 3 will get us 0. 15 plus 2 will get us 17. And -21 plus 4 will get us -17. Let's rewrite our matrix. So first row stays the same. And here we'll have 0, 17, and -17. Now our next step is to get this to become a 1. So what can we do for this one? Well, we have 17. The easiest thing to do will be to multiply by 1 over 17. So we'll have 1 over 17 times row 2. So 1 over 17 times 0, 1 over 17 times 17, 1 over 17 times negative 17. Well, anything times 0 is still 0. 1 over 17 times 17 is 1, and 1 over 17 times negative 17 is negative 1. Rewrite the matrix. So 1, negative 5, and 7, and 0, 1, negative 1. Now we can solve the system because we're going to rewrite our matrix as a system of equations. So here's our system now. We will have x minus 5y equals 7. And then we have y is equal to negative 1. So we can sub y equals negative 1 back in. We get x minus 5 times negative 1 equal to 7. So x plus 5 equals 7. Subtract 5 over, and we will get x is equal to 2. That will get us x is 2, y is negative 1 as our ordered pair, as the answer to our equation. And again, you can check that back into the original system to make sure it works. All right, so that's with 2 variables. Now we're going to go do one with 3 variables. The goals are still the same. We just are going to add that third row that we talked about at the beginning. So this will be example 3. We're still using matrices and the Gaussian elimination to solve it. So here's our system. So we have x plus 2y plus z is equal to 2, negative 2x minus y plus 2z is equal to 5, x plus 3y minus 2z is equal to negative 8. So now let's write our matrix. So we're going to have 1, negative 2, 1, 2, negative 1 and 3, 1, 2, negative 2, and then 2, 5, negative 8. So we're still writing all of the coefficients, putting the bar, and then putting the constants on the other side of the equal sign to make the matrix. It is just a bigger matrix, but the things are still the same, what we're trying to do. All right, first goal is to get a 1 right here. Woohoo! We already have a 1 there. So our next goal is to get this to be a 0. So how do we make a negative to a 0? We add 2 to it. So we can take 2 times row 1 plus our row 2, and that will become our new row 2. So negative 2 times row 1, not negative 2, positive 2 times row 1 will be 2 times 1, 2 times 2, 2 times 1, 2 times 2. So that gets us 2, 4, 2, and 4. And then we're going to add a row 2. So negative 2, negative 1, 2, and 5. So 2 minus 2 is 0, 4 minus 1 is 3, 2 plus 2 is 4, and 4 plus 5 is 9. Rewrite our matrix. So we have 1, 2, 1, and 2. Now we have 0, 3, 4, and 9. And then 1, 3, negative 2, and negative 8. All right. So now that we've got this to be a 0, we need this to be a 0. So all we have to do is subtract 1. So I can just take negative 1 times row 1, add it to row 3, and get our new row 3. So negative 1 times row 1 plus row 3 will equal the new row 3. So negative 1 times row 1 gets us negative 1 times 1, negative 1 times 2, negative 1 times 1, negative 1 times 2. So that's negative 1, negative 2, negative 1, and negative 2. And then we'll add row 3, which is 1, 3, negative 2, and negative 8. Negative 1 and 1 will get us 0. 3 minus 2 is 1. Negative 1 minus 2 is negative 3. And negative 2 minus 8 is negative 10. Rewrite our matrix. So 1, 2, 1, and 2, 0, 3, 4, and 9, and 0, 1, negative 3, and negative 10. So we've only, again, changed one row at a time, and that is our new numbers. So now we are looking at our next goal. So our next goal is to have this become a 1. But if we look at row 3 has a 1 there. So what we can do is just swap these two rows, and that way we'll already have a 1 there. So we're going to take row 2 and swap it with row 3. So we don't have to do anything but change the matrix. So we have 1, 2, 1, 2, 0, 1, negative 3, negative 10, 0, 3, 4, and 9. So we've done everything is the same except these two rows switch places. So it's just like moving the equation at the beginning. This is okay to do because it'd be like taking these two equations and putting this one as the second one and that as the third one. That's basically all we're doing there. All right, so we have our 1, 0, 0, 1. Now we need this to be a 0. We can't use row 1 anymore to change our values, because if we multiply by anything on here and then add it, these won't stay 0. So now we can only use row 2 to get us a 0 on row 3. So we're going to use row 2. We need a negative 3, so we'll multiply row 2 by negative 3 and add it to row 3. So negative 3 times row 2 plus row 3 will find our new row 3. So negative 3 times row 2 will get us negative 3 times 0, negative 3 times 1, negative 3 times negative 3, 0, yeah, okay. And then negative 3 times negative 10. I'm like, that seems too much. So this will get us 0, negative 3, 9, and 30. And then we'll add row 3, which is 0, 3, 4, and 9. So 0, 0, 13, and 39. So we've got the two zeros that we still need for our beginning there. And rewrite the matrix. So 1, 2, 1, 2, 0, 1, negative 3, negative 10, and now we have 0, 0, 13, and 39. So now we need this to become a 1. So all we need to do is multiply by 1 over 13 to get that to become a 1. So we will take 1 over 13 times row 3. That's all we need to do. So we'll have 1 over 13 times 0, 1 over 13 times 0, 1 over 13 times 13, 1 over 13 times 39. So that'll get us 0, 0, 1, and 3. And rewrite our matrix. 1, 2, 1, 2, 0, 1, negative 3, negative 10, 0, 0, 1, and 3. All right, we have our matrix. We've got it down to that Gaussian elimination goal that we needed. Now we can take our matrix and we can write our system of equations. So here's our system. We will have x plus 2y plus z is equal to 2. We have 1y minus 3z equals negative 10, and that z is equal to 3 coming right off of there. So this is our system. We now know the value of z, so let's sub in. Z is equal to 3. So we'll have y minus 3 times 3 equals negative 10. So y minus 9 equals negative 10. We'll add the 9 over. We get y is equal to negative 1. So now I know z and I know y. I need to find the x. So we will now sub in our z equal to 3 and our y equals negative 1. So x plus 2 times negative 1 plus 3 is equal to 2 because we're plugging in the 3 for z. So x minus 2 plus 3 equals 2. So x plus 1 equals 2, combining our like terms. Subtract the 1 over, we get x is equal to 2 minus 1, which is 1. So what is our answers? We have x is equal to 1, y is equal to negative 1, and z is equal to 3. And that would be the ordered triple that solves our system. And you again can check that into the original system.